Hi, this is Siddharth. So this is for this video is to display the functional simulation of the MIPS processor. So initially we've done the implementation of the various modules, and we've done the port mapping in the top module. So now we wish to run a quick functional simulation to show you the working for the sample instructions given in the GitHub page. So now we will open up the simulation. So as you can see over here, this is the entire simulation done starting from the first instruction. So let's now quickly explain the various. So this is the first instruction in which we are doing a NOR with the R naught and R naught being NORed and being stored in R1. So in the next clock cycle, as you can see over here, it's being pushed onto R1. And in the second instruction, we can see we are doing a R1 and R1, in which your R2 gets all Fs. And as you can see over here, R2 gets all Fs in the second instruction. In the third instruction, we are doing an R2 and immediate with 1, meaning the R3 gets a 1. And as you can see here, R3 is updated with a 1. In the next instruction, we are doing an R0 or R3, in which your R4 gets updated with 1. And as you can see over here, your R4 is updated with 1. In the next instruction, you're doing an R4 or immediate with 2, and the updation is on R5, where R5 gets 3, and as you can see, R5 gets a 3. The next instruction is for a branch instruction, in which it should skip the next instruction and move on to the for the next one. So it basically says PC gets PC plus 8, and as you can see, there is no updation of the data memory. And in the next instruction, we are again doing a branch, but in this instruction there is no the branch will not take place, as R1 is not equal to R2, and it just has normal PC gets PC plus 4. And in the next instruction, as you can see, it checks to see if R5 is less than R4, and if it is not true, it will not branch. So we just get PC gets PC plus 4. In the next instruction, as you can see, R3 gets updated with R0 or immediate with 234, meaning R3 gets updated with 234, which in hexadecimal works out to be E and A. So as you can see over here, R3 is updated with EA. In the next instruction, R1, the contents of R1 is being stored into the data memory at position 5. And that you can see happens over here, where positions 5 and 6 are updated with the contents of R1. And in the next memory instruction, the contents, the 16 bits from memory location 5 from the data memory is being pushed into the register file into register number 6. And as you can see, register number 6 gets 4 zeros and 4 Fs. And in the next instruction, R7 is updated with R4 XOR R5 and rotated left shift by 1. So R7 is updated with 4. And as you can see over here, R7 is updated with 4. And in the next next instruction, R8 is updated with R7 right rotated by 2 and XORed with R7. So R8 is updated with 5. And as you can see here, R8 is updated with 5. In the next instruction, R9 is updated with R8 left rotated by 0 and added with R7. So R9 gets 9. And as you can see here, R9 is updated with 9. And in the next instruction, R10 is updated with R9 minus R8 right rotated by 0 So R10 gets 4, and as you can see here, R10 has 4 in its location. In the next instruction, you can see we have to jump by 1. Basically, PC gets PC plus 8, meaning the next instruction is skipped, and the final instruction is a halt instruction in which the PC retains its values until the end of execution. So as you can see here, PC retains its values throughout. Thank you.